So before we go to continue and talk about finalize that to go on, a few words about the Grand Prize competition. I will, of course, email you this right after we finish this. So here's the definition. With the pointer. Convert the uniprocessor recursive merge sort algorithm to a non-recursive parallel MacSpace algorithm. Show the convincing graph task or task graph. Graphics and text show the C code, execute, sort a random array of 10,000 numbers on 64 cores, show utilization graph in an illuminating fashion, analyze runtime speed up and efficiency of sorting the same array over the 1 through 1024 cores. Back a Word PowerPoint report where you could just add minimum text, with just the output. All code and Excel or Calc analysis. Calc is on Linux and Excel on Windows, in either WAR or zip, and email to both of us. And the first received full report plus working solution, I'll try the solution, is the winner. It really did make sense to, we decided today to do significant amount of work right here, so you can take your time and do it carefully aside. The interesting, well, one place where it is shown, hold on, just a sec, let me get rid of this, and now I can show it here. Sound, I hope. What merge sort is. There are two interesting examples. Very fast network. So it goes on and explain, and then it's really reasonable, but that's the second one I want to watch. The first one I want to watch is the second slide. Is the second one on the slide, and copy from here. This one. That's okay. Yeah, we already showed it, yeah. So, yeah, this is the useful one to take a look at. That was the end of the previous one, and the merge sort, and you see that. So it really makes sense of how it works. So we've seen that. The other things shown on the slide are text on the internet, Wikipedia, or just a second. Let me get rid of this. And by the way, here they are. This one shows nice graphic picture of how it operates. This one has a pseudocode in it, if useful. This guy, they're all pointed on by this. C++ or Java or Python, whatever your fancy language is, take a look. And this is Wikipedia with, yeah, just a little bit graphics on the right-hand side, but full explanation of why and how. Merge sort is really very elegant in how it works. And the key job is to take a single processor recursion and turn it into a parallel non-recursion, because doing recursion on parallel machine is much less, makes much less sense than doing non-recursion, so this is the exercise. Going back to our code, what I had here in my copy of sample 2 seems like there are 2 other versions in the code that you have. Here I have if, def, set time, then define the runtime and so on, and everything that's related to counting time is enclosed in if, def, and if, and then I had to add the define set time step. In some codes, it was the same code, but without the if, def, and end if, so you don't have to define. In other codes, all these lines were missing, even the entire computation, or like here, the entire computation of runtime plus equals multiplied by 4, multiplied by 6, and so on. All this was missing, and you only have the original. So what I'll do is, with the same email, I'll also send you this code, and you can just plug it in here and continue. So I want to take advantage of this and continue the explanation. This is about where we took off right before lunch. And we were left with one question, and John gave a hint that he knows what to do here. Other people have ideas. Maybe Patrick already seen it before, but others may have ideas why 1024 cores only execute at speed up of 997, and there are what? 24 plus 3, 27 processors short in the speed up. Anybody had ideas? There are many different reasons, subtleties, right? So instead of guess game, we go on and we'll see that. It becomes more and clearer in the next example, which is sample 3. Same matrix multiplication. But now we want to do better. So what happened in the previous one, I'm going back to the text. Well, let's go to the original text of sample 2, matrix multiplication. The task was extremely simple. A loop, not a loop, just a single multiplication adding to, well, there is a dot product, so if the matrix is 100, so 100 multiplications and additions, and then storing the result. So that's very short, and if it's really short, then we pay a lot of overhead probably for going there and doing too little work. Remember yesterday we talked about the overhead? One of the overheads is the fact that this looks like a function in C. So there is a prologue and epilogue inside the code of the function of saving all the state and building the stack and then doing the operation and then returning from function, which means recovering the contents from the stack and so on. And in addition, there could be overhead in the scheduler itself depending on how we implement it. So to reduce the relative importance of overhead, we may want to increase the amount of work, useful work, that we do in a task. So the relative percentage of overhead will be diminished. And in this case, we do it with sample number 3, only n tasks. Each task now computes a column of the result. So the beginning looked very much the same, And the program start is very similar, except now I use sRand for seed of the random number. Maybe I use a number 100, doesn't matter, use any number. And then each time I assign a value into either A or B, I call the random function. And whatever the number is, I do a modulo 100 just for fun. I could do a modulo anything because all these matrices are float. So I can just use the random number as is and insert it into Aij and Bij. And now I get random or pseudo-random matrices. Why are they pseudo-random and not random? Because every time I begin the program again with the same seed, sRand, then I guarantee to get the exact same numbers again and again. So every run will give me 10,000 numbers, well, 20,000 numbers here that look like they are random, but they are the same sequence of random numbers every time I restart the program. So this is nice in order to be able to repeat exact same execution. And now the duplicable is called mm_n tasks in honor of the special thing in this example. I have only a single, well, I have one loop here for k. K is the column number for the same row. So I do it over all columns. Each column, in each element, which is in one of the columns, I begin again. Sum is 0, and I do the dot product of the column times, vector from A times vector from B, and I insert the result into the C matrix. The row number for the C matrix is the same as the ID number. So now I didn't have to compute the I and J, right? I didn't have to say I is known, it's the same as the ID. And J, I go over all columns of the same row. So I don't have the modulo and divide computations of I and J as in the previous example, but rather C, ID, K. I use ID directly. And finishing it just the same, and I ignore here the timing. I still want to use the same set times as previously. By the way, the task graph looks the same, except I made a mistake and I have a capital D and a capital R, but that's just a slide mistake. Maybe it will work also. And in here, the number of duplications or instances is only m size and not the square of m size as previously. So that's very simple. So very small changes in the code. And that's what I get. But before I get this, which, you know, it already shows that the result is bad again, I'll go back and take a look at the code. I'm closing sample 2 with closed project. I'm opening sample 3, right click and open project, pull down the arrow, go down. There are many calc files that I kept from previous ones, but I want to see the task graph. So here it is. Just like we say, regular, duplicable, regular, very simple. Will it draw anything? No, it doesn't draw anything. Go up to the source. Opening the source directory. what do I get? So again, standard things, and I have the 4 lines that define the constants of how long each operation takes. And then initialization with random numbers or pseudo-random numbers. And the initialization is taken out of the equation on the timing by setting the task time to nothing. And now, each instance, the comment says each instance computes multiple outputs, can be configured, number of instances is the same as the number of cores, or can be configured in many other ways. But anyway, in this example, everything is simple. I do the same code as before, but I've only added the runtime statement in the inner loop and the and the current, and also set runtime or increment runtime in the outer loop, and also at the end set the current task time to whatever I have counted on. And function is very, the end is very simple. So all things well, and I am testing to make sure it works with a build. I have to look at the console. It built okay, and do a run, right click, run as, local application, operating, compiling. That's it. It says initializing, and then the program finished. Matrix multiplication was in task. This was the statement taken from the last task. So simple. Let us just go through the standard process. Refresh. After refresh, I'm opening the utilization with the free office. Oh, did it? What did it do? Recovery process. No, I don't want that. I want it to cancel. Cancel. Get out of here. Go back. Oh, here it's starting to move. Worked. Okay. I got 64 core working and then 36 cores working. I can guess how it will look like. I'm deleting unnecessary column and the unnecessary row again. Mark everything. Go to the chart. Take a look. This is what I did. It turns out that a significant time took to do this. Why did we have that? 64 cores running and then 36. Why did we have such a long time on 36? So it's clear what's going on. I have a matrix which is 100 by 100. I'm trying to do this with 100 tests. But unfortunately, I only have 64 cores. So 64 cores run 64 tasks. They are long tasks because they do a complete row of results. 100 dot products. As they finish, I'm starting again, but only the remaining 36 rows, 36 tasks, again for a long time. So the problem is not, does not match the size of the processor. or the processor does not match the size of the problem. What should we fix? The problem or the processor? Of course, we say the problem is given. We should fix the processor. But that's easy in simulators. Usually you are given a processor, you have a chip. And now you're given a program and the program doesn't match. So, you know, we can play either way. Back to our slides. This is what we get. So 64 is right there in the middle, which I just did. And you see we only got a speed up of 50. 50 was a result of, you know, half of the time or so I'm working with 64 cores, and the other half of the time I'm working with 36 cores. And by the way, 50 is exactly the average of 64 and 36. So I'm using all the cores in half the time, and in the other half the time I'm only using 36, so I get 50. That's a reasonable speed up in these non-matching problem size. And the efficiency is 78%. Now continuously, in the beginning I had 100% efficiency, and in the end I have only 36 by 64, it's about 50% efficiency. All in all, it's 78%. And this is the time. And as I tried for so many cores, I get very good efficiency and very good speed up to about 8. And then it starts dropping down, and at the bottom I get lower and lower efficiency, but the speed up is fixed at 100. Why is the speed up fixed at 100? So why do we get a flat line here of red speed up fixed at 100?
Well, because there are more cores than tasks.
Yeah, because there are only 100 tasks to run. So if you do the 100 tasks in parallel rather than in series, you run 100 times faster. It doesn't matter how many cores. Speed up. But efficiency is the speed up divided by the number of cores. So efficiency goes down very nicely in inverse linear way. So when you double the number of cores, efficiency goes to 1/2, and so on and so forth. So you get a little hyperbolic graph here. And you get a flat efficiency, about flat efficiency, but a flat speed up here. And up here, now you start to move your stop move.
I started.
Okay.
So we have to say that, I mean, the memory size grew in MacSpace compared to QI2S. So
Yeah.
it's getting better.
Oh, okay.
In QI2S with tremendous problems holding all the lookup tables in shared memory. And that's what you definitely need to have. Plus you need some additional space for swapping the data.
But I have maybe a higher significant problem, right? Well, let Mali be off. Have a safe flight.
Thank you. Bye.
See you soon. At any rate, there's a bigger problem because Germany worked on certain size images. Now, somebody comes in and says, no, I want much wider images. And all the calculations he has done in what fits in shared memory don't work anymore because suddenly the first image just overflows the memory. So whenever you run against this, you say, okay, wait a minute. Can we decompose the problem? Can we break down the incoming data into smaller chunks so that we can have multiple chunks working inside at the same time? And when we do that, some people come back and say, no, I need a transform of the whole image, or else I don't get, or for example, they want automatic gain control to just change the sensitivity of the camera based on the amount of light, just like normal cameras do. So they say, okay, first of all, we want to integrate the entire image and see what is the average intensity that you get, and according to that, go back and do the processing and do adjust every pixel. Yeah, so you have to read the entire image, which could be millions of pixels, and then, and we only have 4 megabytes.
Yeah, so
And then, and you don't compress, right? You have the raw data. And then you have to go back and start working on all of it, and there is not enough storage.
yeah.
So we say, you know what? There are very smart cameras that look at only certain small spots in the image, and then they determine the intensity and the sensitivity of the camera based on only a few points. Suddenly we understand why. They just don't have enough memory. But can we do that? And the scratch, no, you can't do this. It's not appropriate with the algorithm and with what we need to do and so on. So we run against all these issues, and we have to do, there are many solutions, but we have to be aware of them. So that's why in the slide we put shared memory aware. No, I've seen already too many.
So what's the current intention if the algorithm, the data is too large for the 4 megabyte? What are you doing?
What shall we do?
Yes, currently. What's the intention?
We fix the typo first,
Yeah, no problem.
and then, so one thing, obvious, simplest thing is to work on some piece at a time, but store all the data in external memory. And I showed yesterday there is access to DDR3 memory, which can be many gigabytes. And if that's not enough, then I showed that there is a potential for flash memory, which can be many terabytes. Not very fast, but very large. So that may happen. You may have to do this. A classic example is when you do image compression on real-time images. Image compression takes too long. You just store all the incoming image in flash, and then you take it back in and compress it slowly. That's one thing. The other thing is change the algorithm to work on the fly. And then we have, sometimes it's not just memory, sometimes there is enough memory, but not enough computing power. How do you know computing power? Because you have time limits. You have incoming data at a certain rate. For example, yesterday I talked about a modem. We work on a modem in the communication. And you have packets coming in at the data rate of the communication, and then you have to do a lot of processing to do either modulation or demodulation or whatever. If there is a lot of noise, then demodulation and decoding takes longer time, whatever. So sometimes there is enough room, but not enough time. So we take a second chip, put next to it, connect them with high-speed serial links, and then ideally, if the processing of one packet is independent of the processing of the next packet and so on, you just multiplex the packet. So one incoming packet goes to processor A, and the second packet goes to processor B. By, the first processor, one processor, does the multiplexing. It says, I keep one packet, I send to my neighbor another packet, and so on.
It would be impossible to do a pipeline.
So before a pipeline, I'm just putting a multiplexing. So maybe you need 3 processors. So one processor receives all the entire stream and then distribute it. 1, 2, 3, 1, 2, 3, 1, 2, 3, like shuffling cards. Okay? And then at the end, after everybody finishes their packets, they all bring it back to the first processor, and the first processor will take them from 1, from 2, from 3, from 1, and combine them into a single stream that goes out. So that's the easiest. And the second one is just like you say, why don't you do a pipeline? So some of the work is here and some of the work is there. And that's just the same. So in system design, that's what we do. Yesterday I've shown how we made a combination of algorithms on an array of 16 chips. It was just like a pipeline, just like you said. So some processors were multiplexed the first pre-processing, and other processors multiplexed the work of compression, and other processors multiplexed the work of modulation. So it's a combination of multiplexing in parallel and pipeline. Very simple. And the job of the software designer is not made more complicated. You still do the same type of algorithm, but if you see you run out of steam, then you add, a little thing to do the multiplexing, and you just duplicate the algorithm. You don't want to write different programs for scalability. And in the pipeline, just the same. So you still program one RC64 for one job, according to these ideas, and maybe you add, in addition, some input-output in a way that I will show shortly. Okay. Number 4, DFT. By the way, the code in DFT also hides the code for FFT, but if we wanted to go over code of FFT here, it will take us 3 more hours, which are very nicely spent, but I don't have. Jamie didn't allow me to stay here until night, so we'll do less than that. Here is DFT. DFT is it's the same order of complexity as matrix multiplication. It's just dot products. Because, where's the pointer? The sequence of n complex numbers, now it's complex, is transformed into n periodic sequence of complex numbers. So we take n complex number and convert them to n complex numbers. And we do it by doing n times this dot product. That's it. But the dot product is the vector of the input times a vector of pre-computed coefficients. And k is the index over the output, and n the indexes over the input. So you see, this is x0, x1, xn. And the output is capital X0, capital X1, capital Xn, small n. So xk, so ak. So xk, xn. And the set of coefficients have 1, 2, 3, 4 constants, I, 2, pi, and capital N, and 2 variable numbers, small k and small n. Euler, only Gauss was in Braunschweig, not Euler, right? Euler was in
Gauss.
No, Euler was in which town? I forget. Never mind. Nobody knows history, science history. Okay, so he formulated this formula. By the way, you know that this formula is an axiom. It works very well with the rest of mathematics, but it cannot be proven. That's very interesting story. There is Euler's equations and so on, but we all agree to use this. So instead of the exponent, we just use cosine and sine, and of course we pre-compute them. And now it's normal algebraic complex numbers where I can separate the real and the imaginary. Using exponent is not easy because it doesn't appear like a real plus imaginary part.
Good question. Why is this an axiom?
Huh?
Why is this an axiom?
Oh, this is a quick question but a long answer. But the best place it is answered, there is a novel in the film, really a nice story film, and it's called like the number pi or the number E or whatever. I'll find point. It's written by Japanese and also filmed in Japan. Japanese lady who wrote the story wrote it maybe 20 years ago when she was 21 years old, and then made a film. It's beautiful.
But
So I get a 2-hour answer.
Yeah. But it can be represented as a series,
No, that's something
as
else.
well as cosine and sine.
Yeah, yes, but these are representations, and you demonstrate that this is correct. But it's not it's not a give you the reason or the original reason. So there are so many demonstrations that this is correct. For example, if you use a series, so you use Lorraine and Taylor series also. Okay, expansion. But I like the movie explanation better than the series. Much more emotional. Anyway, this is the loop. Very simple loop to do discrete Fourier transform. X is complex, 0. This is very close to the syntax we use in C for complex numbers. We can hide all the complexity of complex numbers by a set of macros. And now we use just complex 0. And 2 loops, K and N. K for all numbers, and N is the loop for this summation. Fk complex, so you put the complex in parentheses before every operator that you use. So the plus and the multiply and the product are all complex. We need to decide how to represent the work with complex number. This is if we use the C99 compiler and upwards, we use include complex.h. Everybody, for example, the C compiler that we have in this virtual machine included already is the white compiler, and it has complex.h defined. This is the new .o page that explains the rules. They contributed complex.h. So pre-compute sine and cosine for n and k combination. We have to know what the size of the DFT in order to compute it. So, but there is a lot of symmetry, so we don't need all of them. For example, with 1k DFT, there will be 1n combinations of n and k, but they are symmetric in k and n, and they are divided by n, so that's much less values. We store all the values, or we compute it on the fly, whatever we want in our application. Typically, that's not included in the computation of how much time DFT or FFT takes. We assume that they are pre-computed. Do it once. Jamin has shown SAR application with a lot of FFTs, and of course it runs at real time forever, and you only pre-compute all the coefficients once before you launch, and that's it, when you build a computer. Each output is a scalar dot product, still complex number. Each task can compute one dot product, similar to sample 2 in matrix multiply, for one of the k values. So each task stores a subset of the coefficients, and it receives and reads all n input values. So now we answer the question, what's the storage needed for each, and so on. And we need, let's say, 1k DFT, so we need to store 1,000 coefficients, more or less, maybe repeated. And we need 1,000 input value, 2,000. If they are complex float, a float is 4 bytes. Complex is twice because it has real and imaginary, so we have 8 bytes. 8 bytes times 2,000, that's 16 kilobytes. But the cache, like I said earlier, is only 8 kilobytes. So if you try to do this on RC64, not on this emulator, the emulator takes anything. But if you try to do it on RC64, you immediately run into a problem. Just the coefficients have taken the entire cache. Aha. So, you know, people who do this for a living have found all sorts of tricks, and they can reduce the number with some mathematical computation. So you compute most of them, and then with trigonometric functions, you compute others. Or you store a small number, and you do a little computation per inch. So we replace storage by computation. Computation takes time and power, but sometimes we don't have a choice. Of course, what we do, the first thing we do, we go back to the customer and say, do you really need 1K FFT? Is this really, maybe you can look at a quarter K, 256 elements, and do FFT. And then we start fighting with them, and usually they say, no, we tried on MATLAB, we like it, forget it. Of course, 1K versus 256 is a simple game, but usually David, who just left, showed us yesterday the test case that they do on very large radar, and I think he gave the number, they want FFT of 60,000 numbers. We don't know how to make 60,000, so we round it up to 64K, which is 65,000 something. Very nice, but it's crazy to do this. So we keep telling them, look, why don't you break it into 2 parts? And if they agree, we say, no, wait a minute, what about 4 parts, and so on. And yeah, so there is an algorithmic work on modifying the algorithm to our architecture. That's always the case. Each output is a scalar, we say that, or what about other parallelization, and what about FFT? So I'm not going to answer these 2 questions. FFT is included in the code, I'll show you, but it takes too long. But, it takes too long to explain, but it runs much better. What is, for n element FFT, what is the complexity of DFT? How many, roughly, what order of computations we run in DFT? N squared, of course. Just like we need n squared for every n and every k. And both n and k count up to capital N. So n squared. What is the well-known complexity of FFT?
N log n.
N log n, yeah. So way lower. If n is 1024, n squared is 1 million. N log n is 10,000. So the factor of 100 difference just in this. And it immediately shows, you know, when I run DFT versus FFT on here, even in the same program, you see one is 100th of the time than the other. If the FFT is bigger, the ratio is bigger. Here is DFT. As usual, the task graph is extremely simple. By the way, we worked with David and his people at MacSpace on very complex 2-dimensional FFT. And the easiest, David showed it yesterday, the easiest thing is that the task graph remains very simple. So the most complex one that David showed on the screen yesterday, you can see it in the files that you have, was maybe 5 lines in a task graph. So task graph is simple. There is no need for any complexity. How about a 10-minute break? I've been speaking too much.